My name is Luke Seibold, this is PhyziX, and today we're going to be learning about energy and power. So what's cool about work done is it's actually equal to energy that is transferred. Now energy is going to be a super important concept in physics because it comes across in almost every field, from mechanics to thermal physics to electricity to gravitational and electromagnetic fields. Everywhere you're going to see things about energy. So if you can really nail your understanding of energy, then you're going to have a pretty solid understanding in almost any area of physics. So if this is the case, then we know that energy will also be equal to force times displacement. Now, let's use this to understand a concept which is known as gravitational potential energy. So gravitational potential energy is basically the amount of energy that something could have if it were to be set in motion. So to visualize this, let's think about a skydiver jumping out of an airplane. So here we've got a little airplane, and let's imagine that there's a little skydiver in there. And so the amount of potential energy that the skydiver is going to have is going to be equal to the amount of energy that he would have if he fell all the way to the bottom. So that will be equal to the force he has, so his mass times his acceleration as he's falling, times the displacement that he falls, so the height of the airplane. So therefore, energy is going to be equal to mass times his acceleration, and if he's falling, then his acceleration will be the acceleration due to gravity, which is g, times his displacement, which will be h, because it's the height of the airplane, will be the displacement that he's fallen. And so potential energy, which we're going to write as little EP, is equal to mass times the acceleration due to gravity times height. That's going to be a super useful equation for a bunch of different questions that we're going to have. So let's do an example. Let's picture that this airplane is, let's picture that this airplane is 100 meters off the ground. 100 meters. And our little skydiver is 60 kilograms. And we know that the acceleration due to gravity, or g, is equal to 9.81 meters per second squared. So therefore, our potential energy is going to be equal to the mass, which is 60 kilograms, times his acceleration, which is 9.81 meters per second squared, times the height, which is 100 meters. So if we multiply all those things together, we get that potential energy is equal to 58,860 kilograms times meters squared, because these two meters are multiplying with one another, over seconds squared. And as we learned before, this unit is just equal to the joule. So this shows that energy has the same units as work. So EP is equal to 58,860 joules. Now, as our little skydiver jumps out of the plane, he's going to lose his potential energy. Now, this is because the height is decreasing that he's falling from. So as height decreases, his potential energy will also decrease. Now, the law of conservation of energy states that energy can neither be created nor destroyed. It can only change form. So, where is this potential energy going? Well, as he's falling, it's being transferred into what's known as kinetic energy. Now, this is the amount of energy that the little dude actually has as he's falling. So let's figure out what this kinetic energy is going to be equal to. So if kinetic energy deals with objects that are in motion, then maybe a good place to look would be our equations of motion. So if we look at this, E is equal to Fs. Let's write that down. E is equal to force times displacement. That means that E is also equal to mass times acceleration times displacement. And this is because force is equal to mass times acceleration. Now, where have we seen any of these components in our equations of motion? That's right, we've seen AS in the equation V squared is equal to U squared plus 2AS. There it is, AS right there. So now let's isolate AS. So therefore, AS is equal to V squared minus U squared over 2. And so let's input this back into this equation. Therefore, E is equal to mass times V squared minus U squared all over 2. So if we rearrange that equation, we get that 1/2 times mv squared minus mu squared. Now, our initial velocity is going to be 0 because when he's just chilling in the airplane, his initial velocity is 0. So that means that this entire term is 0. So our kinetic energy is going to be equal to 1 over 2 mv squared, where m is mass and v is velocity. Now, if we think about the units for this, the units for mass are kilograms, and the units for velocity are meters per second. So if the velocity is squared, then the units will be meters squared per second squared. And if you multiply this by kilograms, you get kilograms times meters squared per second squared, which is again joules. So this tells us this is definitely a unit of energy. Now let's talk about the potential energy in a spring. So, a famous physicist named Hooke discovered that the force in a spring is proportional to its displacement times a constant which is known as Hooke's constant, K. Now, Hooke's constant will vary depending on the material of the spring, and that'll determine kind of how stretchy the spring is. So if energy is equal to force times displacement, and force is equal to negative k times displacement, then energy should be equal to negative k times s squared. However, as the displacement is changing, so is the force. So we're never going to have a constant force, and so we're not actually going to be able to use this equation. And instead, we're going to have to use a bit of calculus. Now, if you don't understand calculus, it's not going to matter too much if you're just trying to find out what the equation for potential energy in a spring is. But if you do understand calculus, this is a pretty cool application of it. So work can be found by integrating force over displacement. And so if force is negative ks, then this is the equation you're going to get. And it will be between the point 0 and the point s. So that is going to give us W is is equal to negative 1 over 2 ks squared, s 0. And because if s is equal to 0, then the entire equation will be equal to 0, then therefore it will only be the first component, the s component. So the work done, or the energy, potential energy, is going to be equal to 1 over 2 ks squared. And that's your potential energy in a spring. Now finally, let's talk about power. And so power is defined as the rate at which energy is transferred. And so that can also be thought of as the rate at which work is done. And if this is the case, then that gives us the equation that power is equal to energy over time, or is equal to work over time. So basically, it's the amount of energy that something has, the amount of energy that something can transfer, the amount of work that it does over time. So although something might be doing more work, let's say we got a dude rolling a ball up a hill. Pushing on the ball, rolling this big boulder up a hill. And now the work done in order to move that ball up the hill, let's say that's 1,000 joules. Now, if we imagine that we have another guy over here who might be pushing a much smaller boulder up the hill, he's only using 500 joules, let's say, but this guy does it in a time of 5 seconds, whereas this guy does it in a time of 10 seconds, then the power of this guy is going to be 100 joules per second squared. What am I doing? And this guy is going to be also using 100 joules, because 500 divided by 5 is 100 joules per second. So although this guy is doing more work to get his boulder up the hill than this guy, because they're doing it in different times, the power that they have is actually the exact same. And we have another unit for power to represent these two units, and it is actually known as the watt. And so that's 100 watts. If you remember from before, joules is equal to kilograms meters squared per second squared. So then that means that the watt will be that times per second, which will be times per second, which is equal to kilograms meters squared per second cubed. And that is going to be the unit for power, which is just known as the watt, named after James Watt. Now, as I mentioned before, energy is going to keep coming up throughout physics. So if you're really able to get a grasp of it now, it's going to make physics a whole lot easier than the struggle that this guy is having to go through pushing this huge boulder up a hill.